Okay, let's get started. Welcome, everyone. Today we have Florian joining us, Florian Shkurti from University of Toronto and AI2. Florian and I first met in Amherst at RLC, where we were the only roboticists at this RL conference telling them that RL doesn't matter. I think Florian has won all the awards. I won't go through all of them, but I think the thing that characterizes his work, to me, the best is taking a real problem, breaking it down into principled formalism, and coming up with an extremely clever solution. And so that's what I really admire about his work, and I'm excited to hear what he has to say.
All right.
Take it away.
Thanks so much, Abhishek, for hosting, and thanks everyone for coming. So first of all, I've been in Seattle for about 6 months now, and I should really say that you should be really proud of the robotics ecosystem that you have here in between UW, AI2, NVIDIA, all these companies. It's awesome. It's great. Congratulations. So today, I wanted to talk about the work that we've been doing at the University of Toronto in my lab. So I'm wearing my U of T hat on and not my AI2 hat, although the same questions we're sort of considering and sort of discussing and prioritizing at AI2. So if you want to get involved at AI2, it's an amazing organization, and I definitely recommend that you do. So I will start with a little story of reading this paper from Rand of Cold War fame a few years ago that basically said, how many miles of driving do we need to actually certify that autonomous vehicles are reliable? And it's written by a couple of statisticians, as you would expect from the Rand Corporation. But they were essentially modeling, miles driven and number of interventions per mile, and they were trying to make projections about the future. The entire paper ended up being very pessimistic because they said, given current sizes of fleets, we're going to need hundreds of years and driving millions of miles to actually certify self-driving cars. But the issue is, so it came off as a very pessimistic paper. But the issue is that they were, of the three ways that you have to test policies and autonomous systems, they were only considering one, which is doing on-policy rollouts in the real world, meaning you take your driving system, you try it in the real world, you measure accidents, you do updates based on those statistics. They were completely forgetting or ignoring the fact that companies like Tesla would sort of come and really increase the sizes of fleets dramatically and increase the size of data and the coverage of this data. And they weren't counting on the fact that simulation was also going to take off and become more photorealistic, more physically realistic in many cases, and just our infrastructure for simulation was going to become better. So they didn't count on these two, on B and C. So my talk is about trying to cover some ideas in these two areas, with the hope of trying to be a bit less pessimistic than the Rand paper. So the agenda for today, the plan, is to talk about off-policy evaluation and some interesting connections with compositional generalization in diffusion models, so how the two connect and affect each other. Then I'm going to talk about policy evaluation if you have a video action model. And at the end, I'm going to talk about this idea of transferable adversarial scenarios, so trying to generate edge cases. And then I'm going to close by discussing future directions. OK. So I'm going to start with this paper from my students, Hossein and Mike, which is a collaboration with TRI as well. And it's about the problem of off-policy evaluation. So the idea here is you have logged data from a policy. You do not have access to the policy itself. And you're not allowed to run this policy in the real world. So you would like to figure out, given a target policy, which is the driving system that you want to actually test, how it essentially relates to the log data. And you'd like to figure out what's the value of the target policy, but without running this target policy in the real world either. So you want to figure out the value of the target policy purely as a function of the value of the behavior policy. And to do this, we're going to try to morph the data from the behavior policy to the data from the target policy. Is lighting bad?
Yeah, can people see the screen?
No? Oh, this is going to be bad then.
Yeah, I figured you have like a bunch of dark slides.
Yes.
You know what to do. You know what to do. Okay, good. All right, I'm just doing
Perfect.
stuff.
Thank you. All right.
There we go.
We're going to change to light slides later on. But yeah, seeing the slides is important because then we have math. So off-policy evaluation typically is tackled as an important sampling problem. So you want to figure out the value or the cost of a policy pi, which is your target policy, but you only have samples from the behavior policy. And in robotics or driving, the behavior policy can be driving data from any other human, but it's usually safe data. And you just have to account for the mismatch between the two distributions. So you have to reweigh the samples that the return of the samples that you got from the behavior policy in order to get the value of the target policy. And the problem is that when you do this reweighting, you have to compute this type of density ratio, and the effect of the dynamics sort of disappears. But the discrepancy between the policies remains, and it's a factor. So it sort of multiplies with the planning horizon. And the issue here is that these type of multiplicative factors can turn out to have exponential errors. So error accumulates as you're making this morphing from the behavior policy to the target policy. So that has been called the curse of horizon in off-policy evaluation, and there have been quite a few papers that try to address it. Primarily this one from Chang Liu a few years ago at NeurIPS. And the issue with these methods is that the variance of the importance sampling estimator can grow exponentially, which is bad news. So our paper tries to address this, and it does it in the following way. So one central idea in this paper is that we're going to try to do policy guidance. So we're going to take a model for the behavior policy. We're going to try to guide it to look more like the target policy. And guidance in our case is not just going to be positive guidance. It's also going to be negative guidance to steer the new policy away from the score of the old policy. So if you do both positive and negative guidance, you can show that this is mathematically equivalent to sampling from the target distribution. Now, the reason you can do this is that the effect of the behavior policy disappears, and all you're left is with the factors from the target policy and the dynamics model. So again, the reason why we're not able to just run this target policy in the environment is that we don't assume that we have a dynamics model of the environment, and we're not assuming that we can just execute this policy in the environment because it might be unsafe. So imagine, for example, in healthcare, if you were to execute this target policy and your policy was about administering vaccines, you wouldn't want to be the first patient getting that experimental treatment, right? But you would want to test this vaccination policy based on data you have from perhaps other vaccines or other patients. With that, you would be a bit more comfortable. So in healthcare, for example, these types of methods are really important. But I'm arguing that in robotics, they are also extremely important. So yes, this idea of positive and negative guidance is important because it allows you to sample from the correct distribution. If you do just positive guidance, which is what people used to do before this paper mostly, we show that you're sampling from the wrong distribution. It's a very biased distribution. So I can also show it pictorially. So if your behavior policy, the score of the behavior policy looks like the red one, and the score of the blue policy goes the opposite way, then just naive positive guidance is going to go somewhere in the middle, is going to average between the two policies. And you're not going to get any valid sample from either of the two policies. But if you do positive and negative guidance, then the samples start to look more like the target policy which you care about. So that's one element of the method. The other element is that we do chunking, and chunking sort of chunks of generation, and that allows you to get more compositional behavior. So the idea is that instead of having just one data set, you actually have a composed data set. So you start with this behavior data, but actually you're richer than that because you can get you can get multiple compositions of these trajectories for free. So suddenly your data set augments automatically because of chunking. So an overview of the method is the following. The top boxes describe what's happening at training time. So you have behavior data and partial rollouts. You fit a diffusion model, a diffusion policy on this behavior data. This diffusion policy through chunking can give you actually combinations of the data set. So now you have a richer data set. At inference time, you can do guidance in addition to following the score of the behavior policy. And that allows you to compute the expected value of the target policy. OK? If you want to evaluate this experimentally, we show that on average, this method performs the best in terms of metrics such as log RMSE between the off policy and the off policy, the off policy and the on policy value estimate. It also performs really well in terms of rank correlation, and in terms of the top one policies in terms of regretted one. So experimentally, it seems to do all right across multiple D4RL environments. And to the best of my knowledge, at least empirically, this is the best performing off-policy evaluation method in the literature today. Now, you should be asking things like, hey, is this biased or not? And what's the variance of this estimator? And we have a proof for that, which essentially shows that the bias of this estimator is upper bounded by a small quantity. And the variance of the estimator, instead of growing exponentially in the planning horizon, like what was happening in the importance sampling case, now it's happening with as a quadratic function in the episode horizon, which is good. So we managed to reduce exponential variance potentially to quadratic variance. It is still exponential in the chunk size, but that's not a problem because chunk sizes are small. So that's fine. And that's pretty much Stitch. That's the idea behind this paper. And you can show that in terms of simple D4RL environments, the behavior of Stitch is closer to the target policy than doing full sequence diffusion without chunking, for example. Now, we saw that a major component of this method was this ability to compose parts of the data set together. And one question you can and should ask is, how do diffusion planners or diffusion policies do composition? Yeah, Jesse.
So if you have the variance exponential in chunk size, then what is the trick that, ideally increasing your chunk size helps you, I guess, stitch, right? So how do you trade those two positives and negatives off?
It wouldn't increasing your chunk size be the opposite of stitching because you would only go along with the trajectory?
So yes. So I'm going to talk about the effect of chunk size on stitching in a bit. Yeah. But I think from the formula itself, you can see what's the trade-off and when this trade-off stops making sense in terms of the upper bound.
So
yes.
How many data sets that you would actually do OP on are stitchable versus just different trajectories living in the world,
Yeah, I mean, so D4RL, for example, has maze environments, but it also has more Joko-looking.
Constructed to be stitchable by a set of people who cared about stitching.
Yeah, to make it look good on offline RL.
Offline RL methods.
It's a good question. So we do require overlap between the behavior and the target distribution, but so does importance sampling.
That's right.
But we require it for one extra reason, and I glossed over it. And that extra reason is box number C, box C over there. And that is because we need this reward function, which is trained on behavior data, to be valid for everywhere where there is overlap between the two. So that's, in practice, in D4RL, that happens. So training on the real reward versus the reward model does not produce major discrepancies, but you could construct data sets where that breaks and the method is going to break.
So just confirming what I'm understanding here, like I guess like here you're assuming that your pieces actually induce this sort of connected, they have a connectedness to them. They're actually both relevant to each other, and
Yes.
they contain this sort of Markov assumption underneath.
Yes.
Okay. And I guess you're comparing against what? Like other offline RL?
We're comparing against input. So there are multiple methods that we're comparing against. These methods, for example, doubly robust estimators or important sampling estimators, there have been some at the forefront of policy evaluation. So we're comparing with what was state of the art for multiple years in these baselines. And MB is just model-based, building a dynamics model and predicting what the value of the policy is going to be while rolling that policy out on the dynamics model. Okay. Now, stitching. So diffusion planners and diffusion policies are rumored and shown to stitch. What gives? So from the computer vision community, obviously, this is not a really weird sample. We're accustomed to this by now. But why does this happen and how does this happen? And there was a paper last year from Mason Kam and Surya Ganguly at Stanford, which is perhaps one of my favorite papers from the last couple of years, that has an actual predictive mechanism for A, to explain why this compositionality happens in computer vision models, and B, to actually be able to predict what's going to be composed. But so the summary of their paper is that the main reasons for compositionality, at least in diffusion models that rely on purely convolutional architectures, have to do with locally receptive fields, so local kernels in the convolutional model, and two, with shift equivariance, with some which you can get. And the third one is that you don't do perfect score matching, so you don't minimize your score error 100%. So they rely on the fact that you do approximate minimization. And the question was, do the same conclusion hold for diffusion models for planning, for trajectories? Because here we have other elements as well. We have action chunking, we have replanning, we have data augmentation. So it's not exactly the same setting. But we wanted to see what are the main factors that drive compositionality in diffusion planners, and how to effectively maximize those factors to get the most compositionality that we can, to get the most bang for the buck, so to speak. And the student leading this effort is Quentin. He's actually from Seattle. And another thing to know about this work is that we don't want to just induce compositionality via offline RL, which has been shown. We actually want to induce compositionality just by imitation learning. So
quick question for
yeah.
So I guess Yilun's work suggests that like if you add up scores, like he argues that they like represent the joint, but that's only true under some conditional independence.
Yeah.
You're arguing that like even without that conditional independence, it does something surprising.
Yes. And I'm gonna talk about exactly what's happening.
Okay.
So first, some proof that our diffusion planners memorize, and our definition of memorize is you compare the sample with trajectories that you have seen in the training set. If it's a subset of a trajectory, then it has memorized. But we do this across 5 environments, and all across the board, the most usual types of diffusion backbones, so UNet and DIT, they memorize quite a bit. So what's the issue? If we go by the Ganguly paper and try to modify these architectures to be to have locally receptive fields and to have shift equivariance, then we're going to notice quite a few differences. So that's what Quentin did. He actually took ResNet and he made kernels very small. He disallowed max pooling, which relies on having indexed information about which pixel was the highest. So it's not shift equivariant. So he made ResNet, he designed an architecture that was locally receptive and had shift equivariance. And suddenly you see results like this, where you have novel trajectories being stitched from the existing data set. And now you can start asking questions such as, how does locality of the receptive field vary as a function of the data set size? So as you increase the data set size, you get more induced locality. So you learn to be more local, at least for EQNet. And you can also see it from by visualizing how much attention is being paid in terms of the center state and the entire trajectory. So if the center state, if the gradient of the center state with respect to the entire trajectory is high, then that means that in order to figure out the value of the center state or update it, you will have to look at the entire trajectory from beginning to end. So that's a very wide receptive field. And that's what you see in the beginning of training. But towards the end of training, you see very narrow receptive fields, meaning that to determine the value of the center state, you're actually just looking at the neighbors of the trajectory. So here you have sort of learned locality through data. You don't need to induce it in the architecture. You don't need to force it into the architecture. You have learned it. So that's pretty much what's happening. And you can see that in the low data regime, the receptive fields are large. In the high data regime, they are getting smaller with training. You can also just measure generally compositionality with data set size. And you see that if you are in the low data or medium data regime, making architectural choices that are going to force these two properties gives you a temporary gain. And then after that, as you increase the data set size, these architectures sort of become equivalent because they're all learning to have locality. So you don't need to put equivariant conditions or equivariant, the equivariance property into the architecture itself. You can just learn it. Yes?
Why is it dipping at the end when you increase the...
I don't know. I had the same question. I don't know. Any other questions?
Maybe I'll ask just a numbers question here. Since they all become the same, the dumb things as well as the non-dumb things, like how should I be looking at this? Are you justifying me to continue doing the dumb thing?
Yeah.
Or are you saying that like no, you should do the smart thing? Like what's the takeaway?
What's the message?
What's the takeaway? Yeah.
The message was mostly this is why the dumb thing works. It's not a message about you need to change your architecture.
But this plot itself just says that the dumb thing works, and the previous ones told us why it works. Right?
Yeah.
Yeah, I guess like that's the
overall message.
Yeah.
That's the full argument, right? I guess. Like you're saying that this is the most we can squeeze out of it. And okay.
I guess it may be useful to know where the dumb thing doesn't work. Right? Oh, sorry, Sid, right?
Yeah. I guess like I was going there a little bit too. Yeah.
Like where does the dumb thing not work? Like it's
the dumb thing by the dumb
we
thing.
should probably not call it the dumb thing. I'm so sorry. I started by calling like
work.
amazing algorithms. Bad things. They're all amazing algorithms. I'm sorry if you wrote them.
What we're currently doing as a community, which is generally just using UNet or DIT as the backbones. So it's not a matter of them failing. It's just a matter of I mean they fail in this setting. So clearly they don't compose. So the question is, do you want them to compose or not?
I see.
And if you want them, then you either have to have a large data set, or you have to make architectural changes if you are in the low data regime. Yeah?
Okay.
So you can try to also ablate which one matters more, whether local filters matter more than shift equivariance. And we show that locality is slightly more important. And if you have neither property, then it's sort of bad news. You can also look at this a bit more visually, and visually it's a bit more striking that when you have both of these properties and you query the diffusion planner to generate trajectories from a specified start and end that haven't appeared in the data set, then it's going to try to stitch multiple types of trajectories across multiple homotopy classes to go from beginning to end. Whereas with these variations, when you start losing some of these elements, you just have less diversity. Now, going back to that argument about what's the overall message, if you compare this architecture with what's happening in diffusion policy, then you see similar levels of sort of memorization and creativity, or compositionality. Let me not call it creativity. But they're arriving at this same compositionality through two different ways. One is through architecture, and the other one is through action chunking. So these are two different mechanisms of getting to the same result overall in these environments. All right, so given all of that, let's just talk a little bit about policy evaluation in video models. And this is a project, yeah, hey, Jesse.
So there are multiple mechanisms for which compositionality arises in the CNN paper that you showed, right? So one of them was that it underfits the loss at some point. Do you see that reflected here, like where the EQ net actually, does it perform about the same in terms of actually matching the loss and getting the same, BC success rates, let's say?
Yeah, we did not do those experiments. We basically took that third element for granted, that it's going to be the same across all diffusion models, regardless of what other choices you make. Any other questions? Yeah.
Does this diversity also come at the cost of accuracy? Does the diversity come at the cost of accuracy or performance?
Yeah, it's a good question. I mean, there are some scenarios in which compositionality might be harmful, right? But in sort of maybe planning methods or off-policy evaluation methods, again, as long as you have a reward model that is valid across compositions, it's useful. But yeah, you could identify scenarios where compositionality is undesired. Like in banking, for example, I wouldn't want my financial data to be compositionally generated from some other people, or healthcare, I don't know. Okay, so policy evaluation inside a model. So first of all, the student who did this work is Wei Cheng. He works at NVIDIA, and he's also a PhD student at U of T. Don't ask me how that combination is possible. But he was trying to do, back in 2025, this idea of essentially getting a pre-trained video model and making it action-conditional. So, and then fine-tuning the action-conditional model on some robotics data, rolling out the policy, and asking a VLM whether the task is successful or not. And then he plots graphs of successful predictions, actual predictions from humans or other mechanisms versus the predicted ones from the VLM. I'll spare you the discussion on architecture. I'll just skip it, but I'll just go to the results. And here, for example, for simple push-T videos, the VLM assessment is correct. It agrees with the ground truth assessment. He also made it work with multi-view video predictions. So you have the wrist camera and a camera looking at the robot. And the VLM is producing reasonable assessments here as well. All of these videos are synthetically generated, by the way. And we can talk about whether the model is overfitting on all of these. I think it is, but that's a separate discussion. On RoboMimic, you can also see, for particular tasks, VLMs agreeing with the ground truth assessment in simulation. Could
detail what exactly you did there for the, so you
For
rolled out an action sequence in
yeah,
the
so
video model, but okay.
yeah, so we give the model the first two images from different views. So effectively the first time step, and we ask it to predict autoregressively one step at a time. And for the actions are issued by the policy. So the output of the video model is going in as an input observation to the policy. The policy is generating actions. You roll this out for a few steps, usually just a few seconds, not very long.
And you compare that to as if you did the rollout in your sim using the.
In sim, you can compare it to ground truth, or you can compare it. You can just compare the end result with a successful, execution of the experiment. But yeah, the VLM is taking the entire generated video sequence and saying, is this successful or not? Okay. Now, you also see examples like this where you want to insert the peg in the hole and then hang the tool from the peg. Now, to my favorite part, so failure modes. So there are at least two failure modes here that the community at large has discussed, and that one is hallucinated objects, and the other one is view inconsistency. You will see on the right side, for example, that objects are just magically teleporting to another place. And there is one more failure mode, which is, I don't think it's very discussed widely, but that is that typically when policies issue very, very small actions, the video model is predicting the same, or replicating the same prediction over time. And that loop gets, gets repeated in ways that, it's not clear how to get out of it. But in any case, if you just look at these correlation graphs in multiple environments, you will see that in some cases, correlation is close to 1, which is what you would hope. In other cases, making predictions with Cosmos is good. Making predictions without pre-training Cosmos is, half as good. But overall, I don't want to overstate how, how accurate this is, because it really relies on training on the particular, post-training on the particular environment that you're actually calling the model. So it's not generalizing as a blanket statement. It's generalizing subject to good post-training. You can also quantify the image quality of the predicted video frames, and that's pretty high. For in-distribution rollouts, that's high. As soon as you start getting out of distribution and just rolling out a policy, it's generally less good, but still better than not doing any pre-training, and still better than not involving your policy in the data generation interactively. So I guess in terms of overall quality, you can also plot rank violation statistics between disagreements in ranking between the actual policy and the predicted return of the policy by the model. And you can measure the mean maximum rank violation. All of this, look good in terms of just empirical evaluation. But I think the major issue is that there is this discrepancy between VLM and human annotations, and that sort of can affect your evaluation, the quality of the evaluation itself. So VLMs are accurate in these types of tasks, roughly around 70%. So what do we do with that? It's not very clear, but just in terms of trying this on real data, we still have the same issues we had before, and you can see, for example, that in the eggplant example, the eggplant is sort of jumping on the gripper. The physics is completely not respected here. But at least it's promising, but not exactly working at the moment. So if you actually compare correlation plots with the previous correlations that we had in simulation, they're definitely lower on real data. But it is promising in the sense that there are incentives towards making these video models better. And if they become good enough to actually do good reliable predictions, then we might as well use them to discover different failure modes of the policies that we perhaps wouldn't have imagined. So let's see. Now, yeah.
Go ahead.
No, go ahead, Sid.
In the previous slide, I just wanted a little bit of a takeaway. One of the values of using these video generative models, at least as proposed by the people who build video generation models, is that it seems like a reasonable way to leverage off-domain data. So you have lots of off-domain data available, internet-scale data, they contain dynamics, and so that gives you an opportunity to leverage off-domain data. It does seem like in your experience that off-domain data doesn't seem to provide significant enough lift, or am I reading these wrong? Because it does seem like, it does seem like with the pre-trained weights, it doesn't do that bad. But tell me a little bit more about that. Like, is that hypothesis like completely invalid? Is that hypothesis reasonable that like they do okay with off-domain data?
No, I think the hypothesis, I mean, if you look at the at examples like this, for example, in terms of image quality, pre-training data definitely helps. In terms of the quality of the policy evaluation, the difference is a bit less, but still you do see significant difference between. So the variant you're talking about is the without the pre-trained weights. Yeah. So you still see a significant drop in performance. So I guess the question is that significant enough to warrant the pre-training, the cost of pre-training?
Yeah.
It depends. But there is a difference.
Yeah, I mean, certainly, like, it also depends significantly on the domain that you're testing it on.
Yeah.
Right? Okay.
I would be more worried about how much on-policy data does it require to post-train it from your actual scene that you're trying to evaluate the policy on. That I find a bit more tough to swallow.
Thanks.
Yeah.
How do I reconcile this with the first section? Because the model-based results were not good, right? Like your thing was much better than model-based, but this is the model-based result.
Yeah.
So if that's a bad method, then should I just like never do it?
So the first section, the model-based results were purely on state-based policies. Doing off-policy evaluation on image-based policies is an open research direction. Basically, very few people do it. We're trying to extend our method in that direction right now.
Got it.
So
this
is the stitch method.
The stitching proofs rely on the fact that you have stateful Markovian
Yes.
data available, right? Like that's the point. Yeah.
I see.
Yeah. So we are in different regimes.
Got it. But let's say you figured out some of the detail. I guess it's hard to predict, but is there something different about this regime that makes like all the like bias issues of models not be an issue? Like models have a fundamental issue.
Yeah. So I don't know.
Okay, wait.
But one of the former postdocs in my lab, so she was working on this exact question on how to obtain generalization bounds of diffusion models, because the error that you're going to commit in terms of value estimation is directly proportional to the error of the model. So you might as well try to upper bound the error of the model. Chi has a mathematically dense paper that essentially has this type of story, sort of the same story as pack-based bounds, but they are not exactly pack-based bounds. It's the discrepancy of the data distribution and the distribution that can be generated by the learned diffusion model. And you can upper bound that by things you can measure, compute numerically at training time. And you can upper bound this error. So at least you have some measure of the expected quality of your method. But yeah, I'm not gonna go into the details of this paper. I'm just mentioning it in case people are interested. All right. Any other questions? Yeah.
Kind of on the pre-training note, so when you're not initializing it with the Cosmos weights, do you suspect that it is like heavily overfitting because it's like a 2 billion parameter model and you're basically training on like lift or can or whatever task? So do you suspect that it is mostly just memorizing it?
I would suspect, yeah, I would suspect so.
And is this?
But we haven't done that experiment, so I don't know for sure.
And is the state coverage within the data sets like diverse enough, or is it mostly like expert demonstrations? Like, do you consider, for instance, like near failure cases or any kind of velocity in the?
Yeah. I think there is enough coverage of the bridge data. So it's basically the bridge data set. So you can plot the coverage of that data set and understand what was used to post-train the model. Okay. So going back to this RAND paper, they were missing things like this. So how to turn an existing experience of a robot with existing observations into things that are a bit adversarial and have different weather conditions. So how to turn observed experience into augmentations of the real experience. And this is difficult, but it has become possible. And I think even though there are multiple approaches to simulating autonomous driving data, one of them is just randomly selecting scenarios or selecting deviations from your recorded experience. And the other one is essentially just injecting, editing a model of the world and injecting new cars, new pedestrians, models that are a bit more photorealistic. But I think the question that was missing in all of these considerations is how do we discover these transferable adversarial scenarios? So I want to be able to discover an accident in simulation and have some guarantees that it's going to happen in the real world. And if it happens, then at least I don't have to experience that accident in simulation, in the real world. I can just retrain my policy on the simulated data and make it a bit more robust in the real world. So with some of my students, many of whom are either at NVIDIA now or at Raquel's company, we're looking at attack scenarios that have sort of temporal consistency. So they are attacks over time, amortized over time. They have 3D consistency. They are object-centric. And they follow an idea that sort of looks like this. Of course, the realization of that idea here in this execution is going to be much less ambitious than what actual autonomous driving companies are doing. But the idea is here. So let's suppose you have a driving policy that is vision-based, and it's tasked with following this line. So it does the square. So without perturbations, it's able to do the square. Let's suppose that I model the scene in NeRF, and I try to adversarially insert an object in 3D and render it in 2D for every single location where the car has passed. Now I predict that in this NeRF simulator, I predict that the car is going to deviate. This is only useful if in the real deployment, zero shot, I manage to recreate the same object somehow, and I see the same deviation in the real world. So the attack in simulation is only useful if it replicates itself in the real world. So the way we did this was that we sort of treated it as an optimal control problem, where we have this rendering function. We have a scene renderer, and we have an object renderer. We're trying to compose the renderings of the two. Both of these are NeRF representations at the time. So this paper was 3 years ago. The policy is frozen. The policy accepts the synthetic image observation. We also assume that we have the dynamics of the car, and we're trying to compute the predicted trajectory of the car and the actual reference trajectory of the car that we wanted it to have. So basically, lane following, and we're trying to maximize the deviation between the two. So we're trying to insert objects in the background of the scene that are going to make the car deviate. And we're computing this in simulation. And the things that we're optimizing here are not just the texture, but also the position of where should you put the adversarial object in the scene in 3D so that it is adversarial, as well as the shape, both the mesh and the size of the object. And it sort of ends up looking like this. Yeah.
question about the model also. I'm sorry, please
Yeah,
continue with this and then like finish your thought here and then I can
Yeah.
ask a question.
So replicating the object in the real scene here, since the object looks sort of like lava, it's weird. We could only do it by either synthetically projecting it on the real images or actually having like a sketchy monitor that displays the object. But it sort of illustrates the idea. And yeah, we can talk about your question.
In the previous slide,
Yeah.
if you don't mind, I've spent a bit of time thinking about long-tail discovery, and I guess like I'm asking more about the regularization here.
Yeah.
Because in some ways, if you wanted massive deviation between your realized and reference trajectory, like you can put a mountain that's spewing lava on your road, right? And so the reason why long-tail discovery is hard because like it's very easy to generate very long tails. You could put a mountain spewing lava on the road. It's actually hard to discover long tails that are actually like relevant. So where is the regularization happening there that makes it relevant?
I'm with you. So the dirty laundry is that you only do optimization over some local regions that allow you already have to have a really strong prior of what's going to be adversarial, and you sort of do optimization in the local region. Now, in this work, we didn't address the issue of realism, so it's definitely incomplete. But in follow-up work that I'm going to talk about, it's a bit closer to being realistic. But here, it's unrealistic for a number of reasons. And I'm going to show you, this is a model we learned for sim-to-sim attacks. But if you look at the types of mesh attacks that we have, it's sort of deforming the car in completely unrealistic ways. So we really don't want this, right? None of these objects are going to be transferable. So I think behind this notion of transferable attacks, it just, I think, implies that it has to be photorealistic or physically realistic. So you need to have some type of generative model and be able to sample from the tail end of that generative model if you can.
That's the tricky part.
Yeah, that's the tricky part, to generate candidate attacks here. So that's the actual problem, yeah. But one interesting thing here is that this sort of adversarial retraining thing, where you take the attack, you put it back into the training set of the policy, you retrain the policy, and the policy doesn't commit exactly the same mistake. So that's where we sort of parked this thought for this paper. And then after that, we basically realized that just doing this for autonomous driving is sort of hopeless because some of these companies are going to blow us out of the water. But for manipulation, this is still an interesting problem. So with James, who's a master's student in my lab, we started thinking about the same problem, but now for manipulation. So how would you, given that experience that we had, what would we do differently for manipulation? So we started by, first of all, doing just rasterization and not NERF. No need to deal with the entirety of volumetric representations. Now, if you have, let's suppose you have 3 cameras from 3 different viewpoints, reconstructing these training views with Gaussian splatting is easy. It's proven, it works. Now, the issue is that as you start deviating from these training views, you really have to really stay close. You start seeing artifacts in terms of the prediction. And you can actually sort of visualize or quantify reconstruction quality as you move away from the nearest training view. So this is sort of, again, the dirty laundry of Gaussian splatting. And it still implies that all your attacks have to be local, again, especially if you do novel view attacks. But the type of attacks that we support now are object insertion. Shape splat is a sort of a database of objects that have already been splatted, so we can just insert them into the representation. So that avoids the previous issue that we had where we were generating completely unrealistic objects. Now they come from a scanned database. Object deletion is totally doable because this is Gaussian splatting. It's not a major problem. We can edit backgrounds now in a view-consistent way. We can do relighting, and we can also do novel views, as long as they're close to the training views. Now the optimization looks a bit similar, but a bit different than in the autonomous driving case. One notable difference is that now we're not assuming that we have a dynamics model of the physics of manipulation. We don't want to do that. It's very hard. So what we're trying to do instead is we're trying to maximize the deviation of the actions of the policy from the reference actions. So we assume that we have a data set, images and actions. We're trying to augment the images so that the augmentations are adversarial to the policy, adversarial in the sense that the policy actions are going to be quite different. And we're hoping that this deviation in terms of actions is going to lead to task failure. If you start retraining the policy, the push-T policy with these types of attacks, eventually, after a couple of retraining iterations, after a couple of attacks, it learns to be robust to relighting attacks on policy rollouts. Now, the interesting thing is what happens when you do this multiple times. So you start having an adversarial curriculum. In the beginning, the none categories means not, not attacked, no attacks at all. Let's look at the first policy. The first policy was the policy that was trained from the real data. On unperturbed data, it did reasonably well, above 80%. You perturb the the camera views a little bit, it starts failing dramatically. You change the lighting, it fails even more. So it's a pretty sensitive policy. Then you include these attacks in the training set, you retrain the policy, and now it's starting to become a little bit more robust. It's losing a little bit of performance on the unperturbed attack, on the unperturbed setting. But you do this again a few times, and then it becomes more and more robust. So that's where we're currently at. This is a work in progress. We haven't submitted this anywhere yet. But the question here is, what happens when you do this infinite times? So you are sort of in the worst case of online learning, where your environment is generating the most adversarial attack. Your adversary is generating the worst environment possible.
I have a quick clarification question here. I mean, yeah. I guess one challenge here is that somehow there needs to be a realizability assumption, right? Like that you need to believe that you're not perturbing the world so badly that the policy is actually not realizable. Because all of this, the regret bound will only work if there is a realizability assumption underlying it.
So we are the things that the attack space or the augmentation space is such that the actions, the demonstrated actions of the policy are not changing. So we're changing things in the background. We're changing lighting. The desired actions of the policy do not change. Only the inputs of the policy are changing.
Oh, I'm just saying, if you make the image all black.
Yeah.
Right. Then no matter what policy you're generating, it's just you just don't have enough information content.
Totally.
So somehow you need to change the world while still keeping the core information in the history. So that conditioned on it, you'll still be able to produce a policy.
Yeah.
Which is tricky. Yeah. But I guess if you assume that, then I can imagine you can write some regret bound on it.
Yeah. So that's what Gisong is working on. He's trying to see what happens asymptotically. Do you have no regret? Is this a valid curriculum? And how does it compare in terms of convergence speed to just randomly selecting your attacks? Or how does it compare to teacher-student training, where you sort of select the next most difficult attack that your policy can handle? So that's pretty much what we've been doing. I think in general, in terms of ongoing and future work, I think the questions that are relevant right now is how can this evaluation in simulation guide real data collection? And how does real data collection guide simulation? The first and two are questions that we're sort of going to work on with our collaborators at TRI for the next few years and with Anima Juntar's group at Princeton. And the third question, I think, is wide open in the sense that I think we should have methods that allow us to evaluate policies just based on states or observations from video without actually having robotic data. And I think that's a little bit harder. A lot of these assumptions that we're making are going to break. But that's roughly where we're going with this line of work. So if you have any questions, I'll be around today, but I'm also around in the next few months in Seattle. So happy to chat anytime. Thank you.
We have time for a couple of questions.
Yeah.
For the last part of the talk, first of all, thank you for the talk. And so I was just this is kind of an orthogonal direction, but like I'm curious if like you've tested out, if you identify one attack and you refine your policy to address that, like is there any correlation to like what happens to other forms of attacks?
In terms of whether you get robustness with respect to other attacks?
Yeah. Like if you consider, say, lighting conditions and you improve on that, will that affect my background? Like is there a correlation, something like that?
I mean, we can quantify that, but I think we're also trying to prove that. So we have some leads. I don't think we're there yet. But when we quantify it, it seems like, let's say, doing joint attacks is much more damaging than just doing a single attack. And when you recover from a single attack, it doesn't actually resolve necessarily the joint attack issue. But we haven't measured transfer across these different types of attacks. Yeah.
Can you make policy evaluation, the evaluation of policy evaluation cheaper? Like currently you're like, to actually evaluate how good your policy evaluation method is, you have to run the real thing.
Yeah.
Like or is that just like an ill-posed problem? Because right now you have to run a bunch of real rollouts with every policy evaluation method you propose. So.
Yeah, I don't have any great ideas. I mean, about that. You mean some type of a meta-learned way?
Meta-learned or some proxy or something. Because right now, every time I have to evaluate policy evaluation, it's like a pain in the ass. Right?
Yeah, but the question is, what type of guarantees can we give if we do that? I don't know. I think perhaps a promising result is if you can reliably quantify, the difference between two policies, like a pair of policies, and then you can improve that to be faster. Then a lot of these comparisons might, might be just more efficient.
Yep.
But I don't have any great ideas about that question.
I guess
it's difficult.
One thing you could do is show that it's true under some distribution of dynamics, and maybe the real world is like one of those, but rather than doing it on the real world, show over some worst case distribution of dynamics.
Yeah. So maybe that's where simulation can help you, doing domain randomization, for example, to help you with that. Yeah.
Okay, I think we're actually at time. So yeah, let's thank Florian again.
Awesome.
All right, so that's it.